So today's topic is transient analysis and harmonics analysis for steady state condition, right? So first we would like to discuss about the transient. Transient, when we will discuss the transient, uh, actually this lecture will be, you can find out there is a two different part of this lecture. First one is transient part. When we will discuss transient, we will consider the linear model of the transformer. Even if we consider the hysteresis loss, but we will not consider the actual effect of hysteresis, how it introduces some kind of distortion in our magnetizing current. We will not consider that while doing the transient analysis, right? But before I proceed to the transient analysis, let us have a very simple example of transient analysis. Let us consider a circuit, simple RL circuit with a DC source. Here, as I have mentioned, it is transient, so we must introduce a switching action to introduce some kind of change. And another one with an AC source like Vm sin omega t, right? So let us first consider the DC side. For DC, what we can write? We can write L di dt plus Ri is equal to VDC, right? And accordingly, if you do some more mathematics, you can write it is like just simple, very simple thing, side transposition and all this. Now, if we integrate, we are assuming that L is a time invariant inductor, it's a constant inductor, and if we integrate, then what we will get? We will get something like this. So, if that is the case, then with a little manipulation, you can find out, here you have that I, you can find out that I is equal to VDC by R minus, let us assume a different constant C dash Now, by putting the boundary condition, we can find out this C dash. Like, how can we add an instance of switching? Like, okay, one thing I forgot to mention here, that here we are considering and that switching takes place at t is equal to 0. So initial current of flowing through the circuit was 0. Inductor was initially relaxed. So your IT at t is equal to 0, we can write I0, that is equal to 0, is equal to VDC by R minus C dash. Here this minus exponential minus RTL will result 1. So basically you will get C dash is equal to VDC by R. In a nutshell, your equation or this equation, after finding the value of C dash from your boundary condition, your this equation becomes this equation will become our very popular one, and that collaborates well with our standard understanding that if it is like initially when t is equal to 0, your current I is equal to 0, and if you put t is equal to infinite, then your current I is equal to VDC by R. And that goes well with our own understanding. What was our understanding? That if it is VDC by R, then means during steady state condition, probably in your basic electrical engineering you have 1000 times heard that during steady state condition, inductor behaves like a short circuit. So if an inductor behaves like a short circuit, then what would remain in your circuit would remain the R, and the current flowing through the circuit will become I is equal to VDC by R. Now another thing here is that how to define the time constant. Now if we plot this circuit behavior, we will get a exponentially rising curve like this. Right. Now we can define the time constant. Most of the time we define it as tau is equal to, although you must know all these things, but still I am telling you, this tau we should define it like the time taken by a rising curve to reach if this time is tau, then by tau, or in a nutshell we can write at I tau, it is because here the final value is VDC by R, so at time tau it should reach 62.8% of its final value. How we can get this? If you put this T is equal to means if you allow this product to become 1, then it will give you exponential to the power minus 1, and exponential to the power minus 1, just let me calculate, it will result you just a minute, let me calculate. it will give you exponential minus 1. This term will give you 0.3687. So if you subtract it from 1, what you will get is like point. Okay, sorry, I just made a mistake. It should be instead of, it should be like this. Yeah. So basically, I tau is the time. Tau is the time. Tau is defined as the time constant of your system by which your system reach 63 point of your. Tau is a time. So basically what we can say that we want, or we can write tau is equal to tau is equal to L by R, and this L by R, do remember a basic thing that in case of a circuit that contains some inertial element like inductor, here the time constant L, if you increase the value of L, it will increase the time constant of the system. That means the system will take a longer time to reach its steady state value, right? System will take a longer time to reach its steady state value. Now this is all about the DC case. So for DC we can have a representation, but now we would like to see what happened in case of an AC circuit. I would like to leave the means. Here we are trying to switch on a simple RL series circuit to our source, and I would like to get an answer from you that what would happen if we just disconnect a series RL circuit from a source. What would happen to the current, and if you can analyze it correctly, you will get the answer, especially those who are having some old electrical appliances in their house, like old ceiling fan and old fluorescent lamp. While switching it off, they must have noticed that some spark takes place inside the switch. So how to explain that occurrence of that spark inside the switch? You should think from this transient part while you are trying to disconnect energized RL circuit from its source. See, electrical transient we can have a thorough detailed analysis, but our main focus of this, like in your later stage, you will also need to consider C, because when we will consider an insulator string or something in power system, we need to consider a capacitor. But as the present course is all about electrical machine, in electrical machine it is very difficult to find out capacitor. So as it is very difficult to find out capacitor's effect in normal electrical machine circuit during their nominal operating range, so I would like to confine my discussion within this RL circuit only. I will not consider RLC series circuit, right? So if it is an RL series circuit, then the topic is RL series circuit with alternating current excitation. Now, unlike DC, see, if you see the means time curve of your source, your VDC, you would have a representation like this straight line. If you neglect that any regulation across your source, if you neglect all those means things, you will get almost a straight or the constant voltage value across your load line, or sorry, across your source, and accordingly that constant voltage will appear across your LR series circuit. But what would happen when we will change this voltage to an alternating one like this? Here, try to understand one thing, that depending on our switching, we will have different value of voltage appearing across our circuit. Like suppose at t is equal to, say, this is something where our omega t is equal to 30 degree. So if I switch at omega t is equal to 30 degree, the voltage at the very beginning that will appear across this is something like Vm by 2. At the instance t is equal to 0, I am talking about, if my t is equal to 0 is such that I am going to switch. Try to understand, this is a very important thing, that my t is such that, okay, I forgot to introduce a switch here. When we switch the voltage, it depends, like although you are switching, for you it is t is equal to 0, but try to understand, not for this Vm sin omega t. It has started its journey quite a long ago, means its waveform started oscillating between plus Vm minus Vm quite a long ago. So when you are trying to switch, you are telling that your switching instance is t is equal to 0. But you should not put here omega t is equal to 0. Rather, you should find out that switching, at the time of switching, what is the phase of your supply voltage. In another word, if this is your total supply voltage, let me draw one complete cycle. You can switch at any time. You can switch here, you can switch here, you can switch here. Here, everywhere from 0 to 2 pi, within this total periodic change, you can switch at any time point, and accordingly the initial voltage that appears across your circuit will change, as well as the voltage variation, and that would govern the entire thing, entire transient behavior of your system. So try to understand the difference between DC transient and AC transient. In DC transient you have a constant supply voltage, in AC transient you have a variable supply voltage. Now we must figure out some mechanism to deal with this means variable things, like at any time we can. So what we can do, we can write the same equation, still remain valid for our AC case, we introduce another factor, that is lambda. Now you must ask me that what is lambda, how to measure lambda. I will tell you how to measure lambda. Basically, this lambda, it indicates the phase of the input So basically, lambda is, we can say it is the angular displacement, expressed in degrees between the point E is equal to 0 and the point T is equal to 0 measured. This is very important segment, try to understand. Measured positively So what I have written now, first of all, what is E? I have not yet discussed what is E, and I am writing all these things, and this must this must came in your mind that what is E? E is the effective voltage appearing across this. This is our E. Right. Now try to understand the interpretation of lambda. What is lambda? Lambda is, let me just clear the, what I told you here, that the phase of the input voltage at which is switching takes place, lambda is the angular displacement expressed in degrees between the point where E is equal to 0 and the point T is equal to 0, measured positively from the point E is equal to 0 and d dt is greater than is equal to 0. So what I am trying to tell you, that when you consider your switching takes place, suppose your switching takes place here, so at that point you are having your T is equal to 0. Now how to discuss that whether dE dt greater than 0 or not is the easiest thing if we draw a tangent to this curve. If we draw a tangent to this curve, if this tangent is having a positive slope, then dE dt is greater than 0. We can have E is equal to 0 here as well as E is equal to 0 here. T is equal to 0, we know that at what time, because we have, suppose if you connect one oscilloscope here, you can find out at which time point it is means your LR circuit is connected with the source. But what we need to know is this difference. This is the value of our lambda. So if this is our lambda, then think about it, how this lambda can alter the entire transient behavior of our system. And now think about it, that generally what comes in our mind. Generally it comes in our mind if we can switch at, if we can make lambda is equal to 0, then that would result in the very small amount of current flowing through our circuit, or something that it's means okay, now instead of making weird means assumption and trying to anticipate the effect of lambda without any understanding, try to solve it in the way we solve the differential equation for the DC case. Now for the DC case, let me write the equation once again for our ready reference. It is di dt plus L di dt plus Ri is equal to Vn sin omega t plus lambda, right? Now here one thing is one thing we can do here, that the derivative of this how to express the what we can means instead of trying to write it in this way, let me just try to inherit some knowledge base from the previous analysis. So in previous case, what form of equation we got? It is like, yeah, this one, VDC by R, right? So if this is VDC by R, then let us try to do something like that, in that way. Here only change is that we are having Vm sin omega t. So let us do one thing. Let us first do a side transposition of L, and we will have now see, when we are having this, we can assume that this one is A is, and H is, so we can write it like, as all these are constant, so A and H are also constant. Now the solution, if we try to write it in that same way, we can write now if you are curious about that how to reach this solution, I can solve it, but I want that you people take a little more, and if you people exert a little more effort and please solve it for me. Try to solve it by yourself without looking any book of differential equation, without looking any sorts of standard available web material, because I know you can solve this equation without any problem just by considering the basic, or by just by remembering the basic uh, procedures of solving a differential equation. Now, if you are interested to verify the solution, then I can show you that. I can put it here in didt. What we will have? We will have, if you put didt here, you will get something like sorry. Aha, I got derailed. This is a problem when I just try to copy something from my notebook. It becomes very difficult for me to follow it correctly. So, if we do the simplification, then what we will get? We will get This is I am writing from this one, this just multiplying both sides of the equation by a, we can write it like this. So finally, when we will add these two equations to get back, why I am multiplying this ai, because I want to show you that if we add di dt and ai, that will give me back this term h sin omega t plus lambda. So if I, after considering this I have asked you to find out the value of I by solving the differential equation, but I am trying to show you that this this value is correct. By doing this, if I just plus this 2, then what I will get? See what I will be getting. This term, these two terms will cancel out each other, leaving us with so the solution is correct. Now it is your task to verify the solution, and if the solution is correct, then what we can write it from this line, that I is equal to h e to the power minus at integration of e to the power at sin omega t plus, I am writing here from this expression of I, what I got. Now here you can see, you can spot two parts. One is an integration of a sinusoid with some means some exponential part. However, if you proceed, what you will observe that this steady state part, it will, this is basically we can call steady state part. How to identify that steady state part? Because steady state part must contain some sinusoidal or time varying part. And how to identify the transient part? The transient part must contain some kind of exponentially decaying part only, not any type of sinusoidal part. Now, if you just try to find out the steady state part, what we know that the steady state value I is in a RL circuit. How to calculate? It is very easy. Yeah, here during steady state, this L will offer a steady state reactance value omega L. So our IS will become something like Vm by root under R square plus omega square L square omega t plus lambda minus tan inverse omega L by R. Now, as I said that I is equal to as I said, I is equal to IS plus I transient. So IS is how much? IS is Vm by Z, then sine omega t minus, no, minus plus lambda. What is lambda? Lambda is the instant of switching, minus tan inverse omega L by R. This is your IS. What is the value of I0 minus? It is 0. So what you can conclude? It will still remain 0. So in that way you can find out the value of the transient at t is equal to 0. So basically your ITR, what you will get, what is ITR? ITR is something that is expressed by this so if ITR is something like this, then write it here. You will only get C1 because at t is equal to 0, this exponential will give you 0. C1, how much you will get here? Minus Vm by Z sine at t is equal to 0, this omega t is equal to 0, sine lambda minus let us make it theta. So in a single line, what is your expression? Your expression I is equal to ISS plus ITR. You can write SS, sometimes I write IS, but you can write ISS to make it more clear. The complete expression is Vm by Z sine omega t plus lambda minus theta, where theta is tan inverse omega L by R, minus Vm by Z sine lambda minus theta E minus RT by L. Now think about when you will have what would happen that if we want the transient term to be 0, because if the transient term is 0, then it is somewhat easier for us to handle, and in order to make transient term 0 is only way to make lambda minus theta is equal to 2n pi, n pi, where n is any natural number 0, 1, 2, 3 like this. So obviously we cannot have something like as large as lambda minus theta is equal to 2 pi. So better don't be so do not have that kind of over expectation or weird things in our mind. Now if the RL branch that we are going to connect is highly inductive, then what will happen? The omega L to R, that ratio will be quite large, so theta will be very large. Now that what is the upper limit of theta? Upper limit of theta is what? Upper limit of theta, can it exceed 90 degree? No. So upper limit of theta is 90 degree. Now if upper limit of theta is 90 degree, then it is always means if you know that your circuit is inductive circuit, mostly inductive, only the resistance present in the circuit is due to the conductor resistance used to develop the circuit. then obviously you can expect your theta to be very close to your 90 degree. Then it is always beneficial to switch at lambda is equal to 90 degree. Then you can make sure that transient part will become 0. That is the contrary to our common idea. Initially we had a notion that if we switch at omega t is equal to something like omega t is equal to 0 or like lambda is equal to 0, when the voltage itself is 0, then we can ensure the minimum current flow through our circuit. But what we can see instead, that if we can ensure that lambda is close to pi by 2, that is, we are trying to switch an inductive circuit at when the supply voltage reach its peak value, we are trying to switch our inductive circuit at that moment, or just prior to the means supply voltage reach its peak value in positive direction, we try to switch it. Then we can make sure that the transient part is very small. However, one thing I would like to give you as a food for thought. On the one thing you should notice that even if our transient current is maximum, does it imply always that I is maximum? Because you can see the steady state part and the transient part, they are acting in opposition, apparently in opposition. So if it happens that transient and steady state they try to oppose each other, then we can have a situation where although the individual current is high, but our normal current is low. So here we have considered a case where it is a highly inductive circuit. Highly inductive by means of highly inductive, I want to mention that theta is equal to tan inverse omega L by R is equal to 90 degree. Now you can see that this switching takes place at here it is lambda is equal to 355 degree. We know how to measure lambda. Lambda should be measured from a point where E is equal to 0 and d dt is positive. Typically it is the point where your curve starts, means your Vm sin omega t, if you consider in that way, where your t is 0 or omega t, better to say not t is equal to 0, rather omega t is equal to 0, 2 pi, 4 pi. All these points we should consider for the means one terminal point of lambda, and another terminal point of lambda is which one? The point or the time point at which we are introducing our LR circuit to this system or to this supply. Right. Now what we can see here, it is a very funny thing. Here we are assuming that theta is not 90 degree, rather theta is approximately, here I have taken example from a book where we have considered theta is -85 degree, right? And here what we want lambda minus 3 theta is equal to this is we want to at 270 degrees, so we decide lambda to be 355 degree just to means illustrate an extraordinary situation. This is very rare in reality. It is so if you do this, what you will get, this can also be written like -5 degree, right? So this thing, when we will see what we will be getting, it is very interesting thing. Forget everything. Take a very lagging inductive circuit. So what can you expect? You can expect that your voltage, your current waveform should lag your voltage waveform nearly about an angle of 90 degree. It should lag behind your voltage waveform by an angle 90 degree. So when it is, forget about this minus 5 degree, let us assume this is 0. So what about your current? Your current should also lag behind almost the steady state component of the current. Obviously we are talking about, when we are talking about this leading, lagging all the time, we always mention the steady state component. The steady state component of the current is lagging behind an angle of 90 degree or near 90 degree. So when your voltage is near 0, then your current, your steady state current is almost reaching its negative peak value. Because your voltage is 0, this is a point where this voltage is very small. Means if you consider the exact value at theta is equal to minus 5 degrees, not theta is equal to minus 5, omega t is equal to minus 5 degree, then it is very small value. Or else if you approximately take it is omega t is equal to 0 or omega t is equal to any integral multiple value of 2 pi, then it is basically your voltage is 0 and current is almost reaches its peak value. So if that is the case, then what would happen? Your steady state current will, is about to reach its maximum peak value. Now another thing, what about the transient current? What was the expression for transient current? Expression for transient current was like, let me write only the transient expression, it was Vm by Z. So here lambda minus theta, how much we have taken? It is 270. So it is Vm by Z. So it is very interesting things to note that at t is equal to 0, so at t is equal to 0, your transient is at positive maximum. So what I was trying to say, when the transient current is maximum, then also you can have a situation where your steady state Now think about a situation where we can have a case where we will be having a situation where just let me show, where we will have something that is the most horrible case. Here whatever we have discussed, it's like steady state and transient, they are counterbalancing each other. Can we have a situation where switching will cost us heavily? Can we have a situation? What would happen if you switch somewhere here? Then obviously you can argue that my lambda minus theta will become how much here at say omega t is equal to almost 180 degree. What would happen? Your lambda minus theta is, if you want, it will become still 90 degree if you want. Then it is like you are switching lambda minus theta. So lambda is equal to, say, if we take 175 degree, what would happen? See, your voltage is 0. Again, try to follow my word. Voltage is 0 at this point, but current would, the steady state current would lag behind it by an angle 90 degree. So steady state current reach at its maximum value, while your transient current, that is always positive, means it only depends on the sign lambda minus theta. So if you give it a positive component, so both of them will reach a very high value at the beginning. So that is very dangerous. So you should try to avoid occurrence of things like that. Right. This is your steady state component, this is your transient component, and the resultant current is this shown by this solid line. So you can figure it out here. Okay. But one thing you should keep it clear, that transient term, that initially it will start with 0, but how, means our interest is that how it change its shape, like how it reaches to its peak, and how it later on how it means. Here you can see that initially resultant current is very peaky in nature, right? But if we can switch somewhere here at, say, when it is like if we have to figure out that where we need to switch, when we can make sure that this means rise is minimum. And the easiest way to do is to minimize this transient term, not to make lambda minus theta is equal to 90 degree, rather to make it as small as possible, although they are opposing each other here apparently. But later you can see that due to the presence of this, after this point, here see the huge change in this resultant current. So if you want to change this result, means if you want to control this resultant current, the only way is to minimize this transient term, because steady state term you have no control, it is governed by your. So if you want to minimize the current shape, it is always better that you do something like doing lambda minus theta is as small as possible. Then only you can keep the transient value very small, and that would ensure minimum means change, or means you won't find any tangible change between your resultant current and steady state current in the beginning. So with this, I would like to end this first part, the transient. Here once again I would like to mention that we have not yet considered any kind of nonlinearities present in our system, but later on we will see when we will analyze harmonics. Harmonics is only applicable to steady state conditions, steady state analysis. But in order to include harmonics in our picture, we must consider the nonlinearities in our account. So if you get confused, hopefully all of you have already become pretty confused with whatever I said, and I'm quite sure that those who had watched the video completely will also find the enthusiasm to figure out what I said, and if there is any contradiction, then how this contradiction appears in reality, or how to means whether it is actually not a contradiction but it appears as a contradiction. So they can figure it out.